words about our speaker. Alessandro Laio has his background, or he did his degree in nuclear engineering and then moved to do a PhD in condensed physics at CISA. And then he did 6 years of postdoc at ETH. And after that, he was appointed full professor at CISA in Trieste, Italy, where he's been a professor for statistical and biological physics and now also for data sciences. His work has been covering a lot of different areas, from biological sciences to now a lot of development of analysis for complex data. And today's talk is going to be about identifying informative distance measures in high-dimensional feature spaces. So thank you, Alessandro, for joining us, and the floor is yours.
Thanks very much. As Clara correctly said, I actually changed the topic of research a few times during my life. This is not going to be the last, but okay. So here today, I'm going to talk about this specific issue, which is, even if it looks very weird, as you will see, it is strongly related to applied data science. Okay, so this is just an overview of what I've been doing in my group in the last 10 years. So this is about, well, broadly speaking, developing tools which allow analyzing high-dimensional data landscapes. So these high-dimensional data landscapes can be those spanned in molecular dynamic simulations, but also like if you have a gene expression experiment, you have 20,000 genes, and this is also an high-dimensional data landscape. And also a high-dimensional data landscape is the pressure as a function of time in atmospheric sciences, and you name it. No? So we developed several tools which allow, in a way, studying these data landscapes with unsupervised method. Like, for example, you can compute the efficacious dimension of this landscape, and so on and so forth. Okay, so here, all of these methods, this pipeline, which include many things of which I could talk about, actually, well, has the, let's say, is explicitly constructed with the specific goal, which is performing this analysis without performing an explicit dimensional reduction. So it's very different from principal component analysis, which is somehow the holy grail in this field. But on the other hand, now, so actually what brought us to try to move forward is actually an issue which is actually extremely important in machine learning and data analysis nowadays, which is the issue of interpretability. Namely, not only you would like to perform your analysis and obtain, well, hopefully reasonable results, but you would like to understand what your result means. What does it mean that you have 5 meaningful variables? What are these meaningful variables? No? So basically, the question that I will try to address in this seminar is which variables or specific features among your data set are the important one to define your data manifold. Okay, needless to say that you are very welcome to interrupt me whenever you want. But okay, so here, now I would like to, okay. So the question that we are trying to address is the following. Given a data set with many features, one can define several different distance measures using subsets of these features. Let's try to go immediately on an applied example. So imagine that your data set is a data set of clinical records. So, so I have basically I want to define how similar two patients are. So this I can do using their blood exam, using their TC scans, comorbidities, genome-related information, or clinical history, or in principle any subset and combination of those. So there are infinitely many manners of telling how close two different patients are. So the question which we try to address is, can we find a distance between patients, which is built with a fraction of these variables, capable of predicting all the others, right? So this thing will, in a way, allow us to condense the information contained in a large heterogeneous data set in, let's say, a single distance measure. And this would be, of course, very, very useful for understanding what the data set tells us. No? Okay, so here, how does so here, okay, so addressing this question in its full generality is, of course, pretty difficult. We may made some step forward. We are not maybe yet there. But let's now try to address somehow a simpler question. Let's say that I have a data space and I only have two distances, A and B. And now I would like to identify whether one is more informative than the other. No? So I have two different manners of telling if the patients are similar and is there one of the two distances which is more informative than the other. Okay, what does more informative mean? Let's try to make an example. So this is, of course, a cartoon. So let's say that here I have a two-dimensional thing. Here this is cholesterol, and this is glucose content in blood, right? Totally invented, no? So here you will immediately, all of you will immediately see which of the two is more informative. And actually, well, the answer is glucose. Now let's try to see why. Okay, so here I have in principle a fully informative distance, which actually uses both variables. But now you immediately realize that if I use only cholesterol, no, sorry, only glucose, then if the distance on Y is small, also the distance in X is small, right? So this means that if I know the cholesterol content, I'm also able to perform a prediction on, so on glucose, I'm also able to do a prediction on cholesterol. But if instead I use only the other, well, actually no, because if the distance in X is small, the distance in Y can be large. No, so these two distances are not mutually predictive in the same manner. And actually this asymmetry in their predictivity actually comes from a very specific geometric feature of the data manifold, which is curvature, right? If this thing was a plane, this thing wouldn't happen, right? So here this is actually due to the fact that this thing is a curved manifold. Clear so far? Okay, so here there is an asymmetric info between the two, and basically, well, we can say that the distance, well, here these are just a manner of saying that Y is more informative than X. Okay, so here, now the thing is how do we actually perform this analysis? This is just a qualitative cartoon, but now the key challenge in this business is that we want to compare distances which live in completely different data spaces. Like, for example, imagine that on one side I have TC scans, so I have features extracted from a neural network, and on the other side I have blood exams. How do I compute and compare distances in these completely different spaces? No, so here I cannot simply compute a number like the Euclidean distance and say small or large. It doesn't mean anything. No, and this is actually. Yeah, so instead of doing it with plain distances, we do it with distance ranks. Distance ranks, what is distance ranks? So here, so I have a space A. So in this space A, for example, I look at data point I, and I say that the nearest neighbor of data point I is data point J. So I have a distance rank matrix, which is Rij A, which is equal to 1. Clear? So here I'm simply looking at neighborhoods, and this the rank is something which is just an integer number, which I can define in any distance space. Now I move to another space, and now in this other space, data point J will not anymore, for example, be the first neighbor, but it will be the third nearest neighbor, no? So basically my distance rank has changed. But actually this change, I can compute distance ranks in any space, right? So, and so I can compare compare distances which live in a completely different units of measure, different spaces, different everything. No, so I'm simply using ranks. So this thing is, okay, so this is a technical thing which I'm going to skip. It's related to a so-called copula transformation on the original variable. Okay, so we basically, what we do is we use the ranks to identify if a distance measure is more informative than another. So how do we do it in our example? So basically for each, for each data point, we, for example, we use as a reference distance y first, and with distance y we find the nearest neighbor, which is this data point here. Okay, then according the nearest neighbor according to y is the fourth nearest neighbor according to x, because here you see that there are according to x four data points which are closer than x. This is just an example. Then okay, so then we do the reverse for x, right? For x, the nearest neighbor happens to be this guy up above there, because it has the x coordinate which is close to it, and the nearest neighbor according to x is the 35th nearest neighbor according to y, right? So basically, in this specific case, y is more informative than x, because the nearest neighbors according to y are also among the nearest neighbor according to x, right? Well, the reverse is not true. So you have this asymmetry in the information content in the two distances, which actually percolates in how these ranks are changing by going from one distance measure to another. Okay, so now we are ready to define our statistics, the quantity that we measure. We call it information imbalance. And well, basically it works more or less as I have already told you. So basically, so I have two distance measures, A and B. And for these two distance measures, now I have two rank matrices, Rij-A and Rij-B. And then basically, so here, informally, the information imbalance between A and B is the average of the ranks according to distance B of the first neighbors according to distance A. So basically, for each data point, I find the nearest neighbor according to distance A, and then I find which neighborhood it is according to distance B, and then I take the average of this number. Game over. Only this. So this is just the definition in equations. So here you are basically summing over all the pair of points under the restriction that Rij-A must be equal to 1, so they must be nearest neighbor according to A, and then I take the average of the rank according to distance B. Okay, then this is a normalization. These are just normalization factors, which are defined in such a way that basically, yeah, this is something that is important to remember. So basically, this quantity which you are computing is, so I can have actually four important different cases. So basically, if this delta is small from A to B and also small from B to A, this means that these two distance measures are equivalent. So namely, if the nearest neighbor according to A are also the nearest neighbor according to B, and vice versa, the nearest neighbor according to B are also the nearest neighbor according to A. No? So this two distances are equivalent. If I am in such a condition, I can throw away one of the two, right? Because clearly I am adding useless information in my system. Okay, now the other important case is if, okay, so here if this information imbalance is equal to 1 in both cases. So here 1 is an arbitrary number which you have chosen. It is set by just our normalization factor. So when does this thing happen? This happens when the nearest neighbor according to distance A is a random neighbor according to distance B. So this actually means that the nearest neighbor according to A in distance A will be just a random rank between 1 and n minus 1, right? And then basically this information imbalance will be the average value of a random number between 1 and n minus 1. And then thanks to our normalization factor, I get 1. So in this case, it means that the two distances are unrelated with each other. So basically, they really like provide information on spaces which are orthogonal with each other. Okay, now the most interesting and important case is actually when A is more informative than B. And so in this case, I have that one of the two information imbalance is small and the other is large. So like in this case, if I am in this two-dimensional plane, which we call the information plane, or I don't remember how we call it, basically you are above the diagonal. So this actually means that the information of B is contained in distance A, which once again means that I can throw away B, right? Because actually A already contains that information, right? Okay, so this actually, this qualitative cartoon, in a way, is the basis of our procedures for performing feature selection and dimensional reduction. So basically, we actually aim at finding the most low dimension, yet maximally informative distance measure among a set of possible distances. So here the important advantage of doing it in this manner is that our distance measure will be finally built with features which have a name and a surname. So you are not combining features with complicated functions like you do in a neural network or even with PCA. There is no linear combination of features. You are simply choosing a subset of features which is maximally predictive of all the others. Okay? If there are questions, please interrupt. All right, so now I go quickly through to some examples.
Like relative to doing principal component analysis, is there some issue with like global versus local?
Yeah, well, this
information.
is the local. This is a very good question. Principal component analysis is something which assumes that your dataset can be globally embedded into an hyperplane, globally. So this thing looks only at local neighborhoods, and so this thing only implies that you are locally able to, if you're that you're able to perform a local prediction of neighborhood. So actually, this is more local, in fact.
Thank you.
All right. Now, a few examples here. I go pretty quickly. This belongs to my old life. Yeah, like I have silicon clusters, and well, the structures of the silicon cluster is described by, okay, in this case, SOP descriptors, which are just variables which are rotational and translational invariant and also permutational invariant. So if you change to atoms, you get the same number. No, so these are very, very good descriptors which are at the basis of a lot of machine learning analysis on that. Now, the question is, can the system be described with, say, only two coordinates? This is the question which we try to address. Okay, so here, how do we address this problem? Here, now we have more advanced method, but this is just to give you an idea of how it works. So we start by computing the information imbalance between each single descriptor and basically the full distance, the one that I can compute using all the descriptors. Okay, now this is what I'm going to get. I'm going to get, okay, so this is our information imbalance plane. This is in logarithmic scale. And I have 300 features. So I have computed, here I will have 299 points, right? Each of these points will correspond to the information imbalance between a single variable and the distance computed with all the variables. So clearly I am above the diagonal, which means that the distance computed with all the variables is more informative, right? But here I can already see that yeah, there will be one feature which will be the one that contains more information than the other, no? Which will be this guy here, right? So I select, I say, okay, I like this feature, so I keep it. And then I add a second one. I add a second one, and then I iterate, adding one variable at a time until I actually migrate to this corner here. This corner here is where the two distances will be equivalent, right? And actually, so this is what happens if I plot the information imbalance between a feature space with 2, 4, 8, 16 components to the full thing. And here you immediately see that in my information saturates with 8 or 16 features. So this means that I can keep only 8 or 16 numbers out of these 300, and I get exactly the same information. And in fact, if then I use exactly these 8 or 16 features to train a model, I basically get exactly the same performance that I would get if I would use all the 300 features by performing a suitable regularization. So here this means this allows me to produce models which are much more compact in their input. Okay, here then, well, this we then worked actually hard in order to make this optimization procedure more efficient, because here, so if I do it in this manner, well, there is an assumption, this is a greedy algorithm, because basically there is absolutely no reason why the best combination of variables should be both built in such a hierarchical manner. No? And here actually we managed to rewrite our information imbalance basically in a manner in which I can optimize it with gradient descent. So this thing is very, very important in machine learning, because we can use all the tools of automatic differentiation and mini batching and all the machineries which are available. So here there is just a trick which I'm not even going to comment upon that, but this thing allows us to do something which is actually what we are doing now. What we are doing now is that we are basically, in general, working in very high dimensional space. So imagine that now, for example, we are working with 20,000 genes. And so here now we have 20,000 features, 20,000 concentrations in each single cell, and we want to optimize a distance in this 20,000 dimensional space, which in most of the cases contains mostly noise. Now, so our distance, we make an ansatz on the most informative distance, which is just this one. Here you have just the original features, and here for each feature, I have a weight. So I have a weight. So then if I have 20,000 features, I will have 20,000 weights. And then we find the optimal weights by gradient descent. So we simply minimize our information imbalance. So here in order to actually impose solutions which are parsimonious in terms of number of features, we add in this optimization a so-called sparsity prior. So basically we optimize the gradient by saying, okay, please find solutions in which the number of variables is as small as possible. No? So here, as you can see, this thing is we're simply mapping our search for an optimal distance in a language which is the one that is used commonly in these optimization abilities. Questions? Sort of clear? Great. Yeah, so here these are, okay, just tests, which I'm not going to enter very much into that, but basically we are really able to identify, even in very complicated data scenarios. So these are artificial data scenarios which are built by us with the explicit target of creating problems. No? So we are working with data distribution which are non-Gaussian, and then we have a data distribution which, in this case, can be described completely by these features here, which are non-trivial combinations of monomials. And then we are able to trace back the correct features to describe these data sets are exactly those one, searching in a very large space of possible. Okay, now now something which is once again a little bit linked to the things that to the molecular world, which is finding the best combination of collective variables. So this is something which, if you want to describe a molecular system, so imagine like, even imagine that you have an ensemble of experimental structure. Now, what is the best manner of recapitulating, of summarizing the difference, the way in which these structures differ? No? So this you typically do with what we call collective variable. Like you can imagine, like here I will make some examples, the radius of gyrations or the content in alpha helix or things like that, right? But okay, so there are really many that you want to choose, no? And so how can I choose the best? Okay, so here in this case, I have my target distance is a fully informative distance. So like the full informative distance is, for example, the root mean square deviation between two structures, or you can take the dihedral distance or the contact map distance. These are all equivalent fully informative distances. But however, are distances which live in a very high dimension. So here the dimension of the space in which this distance is living is the coordinates of all the area. No? Very high dimension. And not interpretable somehow, no? Now, this is on one side my target distance. And then on the other side, I have collective variables, which are like order parameter, collective functions, which I compute on my data set, which I can interpret. I know what the radius of gyration is, and so on and so forth. No? So these are interpretable variables. And then I do basically the same procedure. So basically, I optimize my information imbalance. Here is with the lasso penalty. And then this is the best solution: one variable, two variables, three variables, and so on. So here you have to notice, first of all, that this thing does not go to zero, right? Why? Because clearly these features cannot be fully informative, really fully informative on my my distance. So this means that there is still, even if I use all of them, there is still an information gap. There is something which is missed. No? So this also allows you to tell how good your set is, right? If I am reaching. So this number is still pretty good. Still pretty good. And here, one sees that after 4, I have really no information really no information gain anymore. So this thing that these collective variables actually, even if they are different, they actually tell you the same story, right? There is no extra information provided by those variables. No. Now I choose, yes?
It's ready. As this with our capacity to identify the different features. So I mean,
yeah.
So let's say these are redundant, but could we find other pools that could integrate indeed for the missing part?
Absolutely, yes. So the thing is that chemical knowledge is crucial to provide a set of putative descriptors which are informative, which are redundant, but informative enough about your system. Here, in this specific case, as I'm going to show you really in one slide, if you reach this level of predictivity, you basically are able to predict one-to-one all your conformational states of your system and all your barriers and everything. So this is enough information. But this is, of course, system dependent. No, so it depends on your system if this is enough or not. But clearly, in order to do this, you have to start from a very large basis of putative features, right? So this thing does not invent features. This thing selects among possible features the ones which are more important.
May I ask something? Adding to that, like, is that information space very much dependent on the data that went into the model? So what, for instance, was trained on, or is it well transferable, or, you know, you could use transfer learning to generalize to other
Yeah,
systems?
well, so it depends a lot on the field. Of course, we do cross-validation. So here in this specific case, of course, we test this information content on a subset of data which hasn't been used to optimize that. But this is clear, no? But then, okay, now, well, I will tell you immediately. So now, in this specific system, these are the variables that seem to be working better. I can tell you for sure that if I take another protein, I will get a different result, no? But on the other hand, this thing, I will get another result. Like even in gene expression data, there is absolutely no reason why you should get the same genes, the same 10 genes that recapitulate the dynamics of your cell community if you change cell community, right? And so the result is natural that it depends on the system. But on the other hand, if in your specific system, if you have two systems and it happens to be described by the same mesoscopic descriptor, this tells you something on the fact that these two systems are very probably key, right? So basically, this is also an extra information that you get, right? Okay, so basically we are, well, this is just that, okay, so if you basically do, you compute, you do a full kinetic analysis on this system using the original distance measure, which is fully informal, or only these three collective variables, you basically get the same result. So basically the same cluster of populations, also the same barrier, the same everything. So this means that these three variables are actually very good qualitative descriptor and even quantitative descriptor of your system. Okay, now, okay, so here I now have a few things of which I could talk about, because, okay, so we have used this. How many of you are working on represent or neural networks? So because here there are two or three things that I could tell you. One is how to apply this field in studying the representations of data in neural networks. And the other thing is, which is, in my opinion, is maybe more general purpose, is causality. So, because actually we can apply this field to study causality. So how many of you, well, neural networks, maybe not many. One, or well, actually pretty many. Okay, so here maybe I can only zoom quickly through that, and then we will see what we can do. Okay, so basically the thing is the following: that so here there are many things that one can do with this tool of neural networks. This is just one of those. So basically, so these are image caption pairs, which actually include an image and then a description. So these are completely different data, different representation of the same semantic content, right? So basically, what do they have these two things in common? So even, of course, the coding of these two spaces would be totally different, because one are pixels and the other are tokens. But actually, for a human, they provide somehow the same information. So this information is actually semantic, what we call semantic. Now, are we able to really tell that? So now let's say that I take two neural networks. One, which is for image processing. So this thing is a transformer with 25 layers, so I have 25 different representations of this image. And then on the other side, we have a transformer for text processing, which provides me 16 representations of the text. So now these two representations living, of course, they really know nothing about each other. And if this representation have something in common, this something in common can only be related to semantic similarity, right? And so actually what we are doing is using this information imbalance to find out which of the representation of text and image is similar and mutually predictive among the two transformers. And our claim is that this representation is the one which encodes what for us is the semantic. Sort of clear? Okay, now, so this is just the idea. Okay, so here, well, these are some results. I don't think I want to enter into pretty much into the detail of that. If you really want to know about that, you have to talk to me, because we have very fresh new results. But actually, yeah, let's say without going pretty much into the details, well, it exists. The thing is the following: is that it exists a set of layers which are in the middle of my network, which are moderately predictive among each other. So actually, where this information imbalance is actually low. Of course, in the first layers, the predictivity doesn't exist because the two representations are totally different, but then the network develops a representation which is predictive of the image representation for the text and vice versa. You will not be surprised to hear that the image representation is more informative than the text representation, because as we all know, an image has more than 1,000 words. Okay, but here these are really things on which we are really working at the moment. Okay, now another thing in which maybe, yeah, I will actually use the last 10 minutes of my presentation, is how to use this information imbalance. So this information imbalance is actually qualitatively a proxy of what we call causality. Because basically, while, so there is a trivial case in which two variables are totally equivalent, and then in this case, there is no extra information brought by another one. But imagine that you are in a case in which a subset of variables of your system is very informative about another subset of variables in the future, while the reverse is not true. So this actually, qualitatively, this implies that the first subset of variables is a cause of the other subset, right? So let's try to be rigorous on that, a little bit more precise. Okay, so here we are talking about time series here. And okay, so there are a plethora of methods which actually aim at actually doing this thing. Then eventually we can comment on what are the advantages and disadvantages of our approach with respect to those. Okay, but here, okay, so let's make a very simple model of causality. So here I have two dynamic systems acting on two different variables, x and y. So in this case, these two systems know nothing about each other, right? So basically, if I do an experiment on x, y doesn't care, and vice versa, right? Now, there is no causality. Now, if I add a coupling, so this coupling here is linear, but it can be anything, then while x remains autonomous, so knows nothing about y is now somehow slaved on x, right? So in order to know the future evolution of y, I need also to know x, right? Okay, so here, this is the coupling step. So here, so the idea is to measure causality by estimating how the information imbalance changes when measuring x alone, y alone, or x and y together. The idea is actually very, very simple. So here, if I had the blackboard, I could probably be even more clear. Okay, so let's say that I have a reference. So my reference is this information imbalance here, which basically quantifies how good I am in predicting the future of x using x alone. Okay, so this is just, you see that here there is a tau, which is the time given. So here I am attempting to perform a prediction of x in the future. Now the question which I ask is the following. Okay, so here this we denoted with the information imbalance from x at time 0 to x at time tau. It's just a shortened notation. Now, now we add to the space that I use for the prediction, I add y at time 0, right? So basically I use not only x, but I use also y. Now, since x is autonomous, basically y is actually like adding nodes, right? So because x doesn't know about y. And so I'm adding, for example, I want 10 coordinates which are just nodes. Okay, so this actually means that this information imbalance here can only be larger than this information imbalance, right? Only be larger for any value of alpha that I can choose. So these are, I have a variation of this. Basically, this information imbalance which I have by adding also y here must be bounded from below from this field, which I can compute using only x. So this is what happens if my system, x is autonomous. Okay. Okay. Now, if instead y is slave to x, adding x is informative of the future of y, right? And so this means that, in fact, in this case, if I try to make a prediction of y times tau, and I add x at time 0, basically it would be useful. This will be useful, and in fact, this number will be larger. Okay? So this is actually the key idea. So is mapping causality detection to a variational principle where I do once again a metric optimization. This metric optimization depends now on a parameter which is the relative importance of the system that I'm testing. And basically, if this system, adding the variables of the system doesn't add information, I will find alpha equal to 0. So a very specific value of our weights. Okay, so this was a little bit of a complex thing, but basically this thing, we tested it on model systems, and this thing works great. Here we are able to reproduce cases in which the coupling is one directional, like in this case. Case in which the coupling is bidirectional, no? Because in this case, they are mutually informative of each other, no? And so in this case, you are able to actually tell where the coupling strengths cross each other in a clean manner. So here this works even in high dimension, and this is actually a difference between a method which well, is considered the state of the art for causality detection in time series, which is this convergent cross mapping. So this is as a function of the coupling strength, what happens with our method in convergent cross mapping. So in this specific case, these are two systems which are coupled only in one direction. So one of the two systems is autonomous. So here, as you can see, in convergent cross mapping, you have the correct ranking, but you have a lot of false positives. So you're actually not able to distinguish the case in which this coupling is bidirectional, in weaker in one of the two directions, from the case in which the coupling in one of the two directions is simply absent. So actually, in fact, where we have a very, very strong added power in our method is in the false positive detection rate. So here, okay, so here I had an example on causality detection on EEG data. Any of you working on EEG or neuroscience? Maybe not, so I'm happily skipping this thing. But basically, we are able to detect causality between different EEG channels, and also causality between EEG channels and the external protocol that I am applying on the subject. Okay, so here with this, I think I can finish my talk, because otherwise I'm afraid to run really out of time. So here I can maybe only one thing that I really want to do is thank my coworkers. Okay, so there are many people who were involved in this thing. Let's say that on the original development of the information imbalance, a key player was Aldo Liemo, who is now making money in Banca d'Italia. So he's really a smart guy, and also his decisions point in that direction. And then, okay, for the causality thing is a PhD student, who taught me how causality is working. I didn't know before working with him, so it was a really, really great collaborator. And Romina is also an extremely talented PhD student who just took her PhD now. And she developed the differentiable variant of the information imbalance, which is actually a key tool for what we are doing now. Now, by the way, Romina is willing to move to the analysis of ecosystem and whatever. So I don't know if any of you is really, well, is working in that field. Maybe I can, give her the comments. All right. No, so this thing I think is gone. I had the conclusion of the summary, which I just leave on for reference. Thanks very much for your attention.
Yeah, so thank you very much for your talk. Now we have time for some questions.
Thank you. So I have probably two questions. First one, I saw at your slide where you were talking about selecting features among the number of polynomial combinations, I think. So my question, feature engineering exists and it brings great results in for some tasks. So did you try to experiment with different kinds of feature combinations, with summations of features, orders and so on and so forth, not just multiplication of features, not just simple polynomials? And the question is it beneficial in some cases, or can you predict which features make sense to combine together in order to reduce the number of dimensions to provide you better results?
So the answer is that the approach is variational with respect to the number of test features you are using. So let's say that you have a result which you get by using plain features as they are. Okay, so let's say that you are happy with the result and then you stop there. Okay. So if you are not happy, then you try monomials, and then you get another number which would be by definition lower. Okay. And then at this point you say, I'm happy, answer yes, you stop, answer no, you go to polynomial. But clearly the more you add, so here there are cases in which, and this is pretty much system dependent. Let me say that so far we haven't really explored in a systematic manner this direction. It's a very limited direction, but in general, the larger is the feature space, the better your result, but for sure. And then systematic manner of enlarging the feature space is feature engineering, where correctly, like combining features in polynomials.
Okay. Okay, then my second question would be like this. I can imagine in real life applications that sometimes there are tasks where in some areas of parameter space, one features are more important, in others are other more informative. So did you try to maybe on some of more complicated cases visualize, well, it's more towards dimensionality reduction, visualize the areas in which one feature is more important than others? So maybe there are like areas where most informative features are different.
Okay, this is an excellent question, because it actually is one of the things that we would like to do. Because basically, our statistics is obtained by summing over all the data. But actually, we have a probability distribution. And this probability distribution can be unimodal or bimodal or whatever model. No? So this we haven't yet explored in the So this is something that, in a way, we would like to see. So we know that it's very easy to build toy models in which this thing happens, but we haven't yet explored it.
And then the third question, how computationally expensive it all, and especially if you would apply it on large data sets, so for practical applications.
So I think is in principle, this case, quadratically in principle with the number of data points, and linearly with the number. But okay, the quadratic scaling actually can be very easily brought to linear in a very simple manner. Because basically, you so let's say that you have 10,000 data points. So what we actually do is not computing 10,000, but we select at random 500 points, we remove them from the data set, and then we compute these statistics only on these 500 data points using all the other. And then we take the average. The major advantage of that is that in this manner, we are taking the average of numbers which are by definition higher. So they are statistically independent. And since we are taking the average of a single number, you need just 100 or 200 points. So here, as a matter of fact, we are currently applying that in data scenario with the videos of data.
And I can imagine, if I understand correctly what you're doing, this is pretty easily parallelized. So you can use it in the parallel algorithms. Okay, thank you.
Questions, yeah.
Yeah, just to see if I understood the point. No, when you talk about causality, you are in a picture like design of experiments. So I don't know, I wish to understand what is the best temperature for a reaction, and then I introduce also the pH and I don't know, salt and so on. No, so many factors and one event somehow, no, the reaction. But if there is something more different, like say, I wish to understand the docking between two molecules and all the parameters that can affect this docking, but then also introduce a different perspective, so different elements. So for instance, the stability that I can have changing something in one of the two molecules making the docking. So is something that is for which I can use the same approach or not?
Well, here I would say that this can be formulated in a manner which is in a way making it possible to address it, because we basically have three different spaces. One is the space of stability, where you can in a way tell how close so space of stability. Then you have the space of affinity, the space of molecular affinity. So here we have these three spaces, and then somehow what you want to find out are okay, the molecular features can be made to measure on available data. Then in the predictor, the question is, so I want to combine these molecular features in order that I can maximally predictive about the distance in space, or a distance separately, a distance in affinity state, right? But then clearly can be so then I will have different features which most probably predicting of different states. No? So clearly combining this is like a Pareto optimization, because basically we want to optimize two different things, no? So which have nothing to do with each other. It's pretty likely to get different optimal features for predicting the two. But on the other hand, you can recast it both.
Using different pools for each of them. Okay, thank you.
Thanks for the talk. I was curious about the EEG application you skipped. Can you give one word? I mean, yeah, because I'm confused about the causality in the EEG case.
In one word, so no, one word, no.
Maybe
but maybe I can show you just one thing. Because basically, so here the key point is the following. So this thing is, okay, okay, so here, so in EEG, what you do is the following, is you expose, which is actually related to your question, sorry, because it's related to how you apply this thing in experimental tasks. So now, in EEG, you have a protocol. So this protocol can be very simple or very difficult, but something that, for example, you show on the screen the sample. So this thing, like in this case, is something which is active for this time window here. Okay? And then in your subject, you are recording a time series. You're recording a time series. Now, so in this case, the different experiments differ only by the length at which the image is shown on the on the screen, right? And so basically, imagine that I measure causality between this time window and this time window. So here the exposition to the image has not finished yet. So there can be no causality, right? Because my subject doesn't know how long the picture will be shown to her, right? While instead in these conditions in which it is after the picture has disappeared, then there can be causality. And so basically, actually, this is exactly what we find in this case. We find that basically exactly on the same data, if I measure causality when causality can exist, namely when basically my subject in this case well, somehow knows implicitly how long the exposition has been, then I have that as a function of time, these are milliseconds, I have that in the visual cortex, I have a first causality wave here and then a second causality wave at a longer time. And here instead, exactly also in the visual cortex, basically I have zero causal effect before the image is finished. So this actually tells you a lot about the strong difference between causality and correlation. No? Because basically if I would compute a correlation between these two quantities, this would be by definition symmetric, and I would not be able to tell it. Okay, so here, I don't know if I replied to your question, but basically what you can do with the data is measure causality of a given event in the future as a function of how far this thing is in the future. Then you can measure causality between different EEG channels. So you take EEG channel visual cortex and then you see that there is a causality between the channel in the visual cortex and the channel in the frontal cortex, which is the one recognized in the body. There is a delay of 300 milliseconds and then there is even a backward causality. Basically what happens in the frontal cortex propagates back to the visual cortex another 200 milliseconds. So there are all these fun causality waves traveling back and forth.
Thank you. Cool.
Okay, maybe one last question and then we slowly move down to.
So like, I think similar to like the last two questions. So it's like, rather than doing just like autocorrelation, you're learning more information from, rather than just doing like autocorrelation for the EKG, you're actually picking out some additional sort of the causal structure of one thing causing the other. In a similar kind of way, I think like for like applications with supervised learning, would it be interesting or useful to combine sort of the differential sort of like loss function that you made for these sort of ranked combinations with some kind of loss on labeled data, right?
It's yeah, we would like to do it. The thing is that the loss is dependent on so why most of the losses between neural networks are basically independent on each data sample. Basically, they are a sum of the data. Here in this case, that for example, we have a mini batch, then we have all it will depend on all the pairs. But this is really so something in which we would really like to work on. We would like to insert loss because this loss would allow actually reducing the dimension of the representation.
Yeah, because it's not just finding a new coordinate system in similar ways to PCA, but then finding the coordinate system that you want to solve some problem.
Because allows you to deal some channels.
Yeah.
So basically, PCA you cannot do it.
Yeah, that's right.
Dangerous in a combination. In this case, you simply to do model distillation in a manner which actually leaves the distance between the activations and touch.
Yeah, and you couldn't do the same kind of application with labeled data in PCA because you don't have this like different. It's not a framework that's set up to have like a loss function like that in any case. Yeah, thank you.
Okay, so let's thank again Alessandro Laio for this wonderful talk. And yeah, then let's go downstairs to have some lunch together and we can continue discussions downstairs, of course.